Welcome back. In my last video, I have shown you how to perform SVD of a matrix in MATLAB. That means you are decomposing a matrix into three different matrices U, S, and V. U and V are orthogonal matrices, and S is a diagonal matrix. Okay, that S is I have shown you in my previous video with an example. If you don't know what is SVD is, just go through that video. It is just a 3 minutes video, just a simple example. And now I'll be explaining you with a MATLAB code how to perform compression using SVD. Okay, here I'm considering a black and white image. Okay, for a color image also it can be done, and I'll show that in my next video. Okay, and this is lena.png. This is a black and white image. You can take any black and white image you have, that is load that black and white image. And what is this double? This I'm just converting it into a double precision numbers. Okay, this is just a small conversion because SVD command in MATLAB doesn't take other values. It takes either single precision or double precision values. Just a small conversion here. Then you're applying this SVD on an input image. Okay, image is nothing but a matrix, right? So you're applying SVD on an image matrix, and you will get back three different matrices U, S, and V. And I'll show you what is this S matrix is now. I'll just put a breakpoint over here. Okay, I'll just put just put a breakpoint over here, and I'll just run this. So what you'll get S. Okay, oh, this is your S. See here, it consists of only the diagonal entries, everything else is 0. So what's the idea here is, we'll just consider either 8 cross 8 block or 64 cross 64, or it is 128 cross 128, and we reconstruct the original image by using only these many entries, only 8 cross 8 or 64 cross 64, not the whole 512 cross 512. So what happens is, this is known as the dimensionality reduction, and it is also called as low rank approximation. That means, what's the rank of the matrix? Rank is nothing but the number of non-zero diagonal entries. That is nothing but the rank of the matrix. Okay, and you're converting it into a low rank matrix by neglecting the other things, by just considering 8 cross 8 block. And the reconstructed quality of the image, as you will be seeing, it is considerably good. It is considerably good. Therefore, it's very useful. SVD is very useful, and the storage space will get reduced. Okay, now coming here, I have used the block size as, I'll just remove this breakpoint. Okay, and now I use the block size as 8. Let's see what is the output we'll get. Okay, I'll just continue. Okay, I get I think it's taking 128 only. Okay, now I'll run this. Now it is taking 8. Okay, I'll just show you. This is the reconstructed image. See, it consists of, it is not equivalent to your original image, because we are just considering 8 cross 8 block in the S matrix for the reconstruction. Okay, reconstruct input image is I. You are converting it into three matrices U, S, and V, and you are reconstructing the original image as U, S, V transpose. Okay, this is your reconstructed image, and it consists of lots of error because we are using 8 cross 8. This is your input image. Now I'll change the block size to 64. Okay, now I'm using 64 cross 64 instead of 512 cross 512. See, now what happens is, see, this is the error, that is the difference between your original image and reconstructed image. Error is, little bit of error is still there, right? and this is your reconstructed image. This is your reconstructed image. Okay, this is almost, you can compare, it is comparable, it is comparable. Okay, this is your input image. Okay, now I'll make it 128. That is, you're considering 128 cross 128 in the S matrix. So what we'll get, error, see see this is error. Error is reducing a lot. That means the output image, this is your output image, this is very much comparable to our input image. That means here you are not considering entire S matrix, you are just considering a block of it, but still your quality of image reconstruction is comparable to that of your input image. And that means you're storing your output image with less memory compared to your input image. See the compression ratio and getting it as 0.5. And you can also calculate the PSNR value, and this is the code to calculate the compression ratio, and this is your PSNR, and this is your error. Absolute difference is nothing but your input image and the output image. And why we are getting the compression ratio as 0.5625? Because see here, you're not for reconstruction of your output image, you're not considering entire U and entire V. Okay, S, it's 128, so you are considering only 128 cross 128 here. Here what, how much you are considering? Here you're considering all rows, that is 512 and 128. 512 cross 128, this is 128 cross 128, and this is 128 cross 512, that is all columns. Okay, you're doing dimensionality reduction. That's why the storage space required for your output image is less than that of your input image, so you're getting a compression ratio of 0.5. Okay, and as you can see from the output also, error is very much less. Okay, that absolute difference is also very much less, and it is a very good, it's very advantage. Okay, it's very much useful, and this is how we can do compression using SVD. Hope you all understood this, and thanks for watching.